Hello and welcome back. The subject of this video is going to be elastic collisions specifically, but just to remind you that all collisions, and I'm talking about elastic and inelastic collisions, momentum is always conserved. So we can set the momentum of the system just before the collision equal to the momentum of the system just after the collision. It's always true. If we have an elastic collision, a specific type of collision, then kinetic energy is also conserved. So for inelastic, we can set the final momentum, whoops, we're using primes for final, my apologies there, P prime equal to the initial momentum, P non-primed. If we have an elastic collision, then we can also do the same thing. The final momentum is equal to the initial momentum, and the initial kinetic energy and the final kinetic energy are the same for the system. So we actually have two conservation laws we can apply for an elastic collision, and only one conservation law that we can apply for an inelastic collision. So elastic collisions, let's take these two equations. Conservation of kinetic energy is 1/2 m, and we're just going to do it for two objects. So this is going to be m1 v1 initial squared. If there's not a prime, that means it's the initial velocity, plus 1/2 m2 v2 squared. So this is the initial kinetic energy is equal to the final kinetic energy. So that's 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. So initial kinetic energy is equal to final kinetic energy. So what we're going to do is take this equation and we're going to rearrange it a little bit. So let's go ahead and move all of the 1's to one side, all m1's to one side and all m2's to the other side. So I can write this then as 1/2 m1 v1 squared. I'm going to move this m1 to the side, so it's going to pick up a negative sign, minus 1/2 m1 v1 prime squared is equal to, we have 1/2 m2 v2 prime squared. And now moving this other m2 term, it's going to be subtracted, minus 1/2 m2 v2 squared. All right, now we're going to factor out the m1 on this side, we're going to factor out the m2 on this side, and notice that the halves cancel all the way across the equation, just multiplying through by 2. And so what I have left is m1 times v1 squared minus v1 prime squared is equal to m2 times v2 prime squared minus v2 squared. So notice this is still conservation of kinetic energy. All I've been doing is rearranging the conservation of kinetic energy equation. I have not changed its meaning. It's still conservation of kinetic energy. This is the difference of squares, so I'm going to unfoil it. So this is m1 times v1 minus v1 prime times v1 plus v1 prime. So that's unfoiling the difference of squares, and I'm going to do the same thing on the right-hand side too. So this is m2 times v2 prime minus v2 times v2 prime plus v2. So this is all right here, Ke equals Ke prime equation. Okay? Now we're going to take our conservation of momentum equation and we're going to manipulate it a little bit. So let's take our P is equal to P prime equation and write it out. So this is m1 v1 plus m2 v2. That's the initial momentum is equal to m1 v1 prime plus m2 v2 prime. So this is the final momentum. We're going to do the same thing. Let's bring all of our m1 terms to one side and all of the m2 terms to the other side. And when I do that, this m1 term will come to this side. So I'm going to have m1 v1 minus m1 v1 prime. And on the other side of the equation, I still have my m2 v2 prime, but now I'm going to pull over a negative m2 v2. Again, factoring out the m1 from the left side, m1 times v1 minus v1 prime, factoring out m2 from the right side, m2 v2 prime minus v2. All right, now I have the equations in the form I want it. Notice that these two equations still is the conservation of momentum equation, okay? So I've not changed it. Now I'm going to combine the two equations and I'm going to stack them suggestively. So I'm going to take the equation I got from applying Ke is equal to Ke prime, and I'm going to place that equation in the numerator. So this is what we have, m1 times v1 minus v1 prime times v1 plus v1 prime. And I'm going to set that equal then to m2 times v2 prime minus v2 times v2 prime plus v2. So that's just conservation of kinetic energy with terms rearranged. This is how we rearranged them, and now I'm just writing it here. And now I'm going to take this equation for P is equal to P prime, and I'm going to place it suggestively just below. So I'm going to take this equation and put it here. So this equation is going to be m1 v1 minus v1 prime is equal to m2 times v2 prime minus v2. All right, so I stacked them suggestively. And that's because I am going to use this great trick of dividing one equation by another. It makes the algebra much less cumbersome. The more difficult the algebra, more room for error. So anytime you can divide equation by another to simplify things, it reduces the percentage chance that there'll be error. So the m1s cancel. The v1 minus v1 primes in the numerator and denominator also cancel. On the right-hand side, the m2s cancel and the v2 primes minus v2s cancel. And what are we left with is something I like to call the relative velocities equation, a very simple equation that says that the sum of the velocities for 1, initial and final, is equal to the sum of the velocities for 2, initial and final. Notice no dependence on mass. Now, when can we use this equation? It's only valid for elastic collisions. Okay? Can't use it for inelastic collisions, and I like to call this equation the relative velocities equation. So I'll refer to it as such when we are solving problems. Okay? So this is relative velocities equation. So the textbook derives a different equation. It's much more cumbersome to use. You'll notice that there's a lot more terms in it. This relative velocities equation, much easier to use. And you know, again, you've not like created a system of 3 equations that are independent by combining the kinetic energy and momentum. You have now 3 equations, but they're interdependent. So it still allows only for a solution of 2 unknowns, even though you have the 3 equations. And by the 3 equations, I'm talking about the conservation of kinetic energy, the conservation of momentum, and now the relative velocities equation. But we can choose which 2 equations we want to use to solve for the 2 unknowns that we're asked to solve for in a particular problem, and we'll be looking at one in the next video. We can choose whether we use this equation and this equation, or this equation and this equation, or this equation and this equation. And you'll see that these 2 are going to be the logical equations to pick because they're both linear in the velocities. This equation right here is particularly nasty because you're dealing with velocities squared. And so imagine solving for a velocity in this equation and then taking what it's equal to and plugging it into the conservation of kinetic energy. You got to square it now. It becomes a big mess. Lots and lots of room for algebraic error. So this relative velocities equation coupled with the conservation of momentum equation make a nice system now of 2 equations to solve for 2 unknowns with when we have elastic collisions. All right, so let's look at one of those in the next video.